Hello there, and welcome to Life Beyond Seen, where curiosity slows its pace a little, where big ideas are allowed to unfold gently, and where learning doesn't have to feel like effort. Wherever you are right now, whether you're settling in for the night, letting the day fade away, or simply taking a quiet moment to yourself, I'm glad you're here. Tonight we're going to drift into a time so distant it barely feels real, a time when the oceans themselves were very different places, and the creatures that lived within them were larger than anything most of us can easily imagine. Before we begin, let me ask you something simple. Where are you listening from right now? Is it late? Early? Somewhere in between? Maybe you're lying in bed, or sitting with the lights low, or letting this play quietly in the background while the world outside grows still. However you've arrived here, you're in good company. And if you find this kind of calm exploration comforting or interesting, a like or a subscription is always appreciated. It helps this quiet corner reach others who might need something slow and thoughtful to end their day. Now take a moment and picture the ocean. Not the ocean as you know it today, with satellite images and shipping lanes and documentaries that zoom in on coral reefs. Think instead of an ocean without names, without borders, without maps. An ocean that existed hundreds of millions of years before the first human thought to measure it. A world of water that covered most of the planet, deep, dark and full of life that followed rules very different from the ones we're used to. Because long before whales sang through the deep, long before sharks became the icons of the sea, Earth's oceans were home to giants. Creatures so large and so strange that even now, with all our technology, they feel almost unreal. Animals longer than buses, predators with jaws wider than doorways, beings that ruled their environments not through intelligence or tools, but through sheer scale. And what's perhaps most fascinating is that these giants weren't rare accidents. They weren't one-off evolutionary experiments. For vast stretches of Earth's history, being enormous was normal. It was expected. It was in many ways the winning strategy. So the question is simple, but the answer takes us on a long and winding path. Why were prehistoric oceans filled with giants? To understand that, we have to step back far beyond the age of dinosaurs, far beyond familiar creatures, and into a world that barely resembles our own. If you could travel back more than 500 million years, you wouldn't recognize the planet at all. The continents were scattered in unfamiliar shapes. There were no trees, no birds, no grass, and no sound above the waves except wind and weather. Life, for the most part, lived in the sea, and the sea itself was not yet the calm, oxygen-rich environment we depend on today. Early oceans were strange places. They were warmer in some periods, colder in others, often low in oxygen, sometimes rich in minerals that would be toxic to modern animals. But they had one important feature that would shape everything that came after. They were full of opportunity. In those early ages, life was simple. Single-celled organisms drifted through the water, feeding, dividing, evolving. Over immense spans of time, those simple forms gave rise to more complex ones. Soft-bodied creatures appeared, then creatures with shells, then creatures with primitive eyes, mouths, and limbs. And as life became more complex, something interesting happened. Size began to matter. In the water, being bigger comes with advantages that simply don't exist on land. Water supports weight. It reduces the strain gravity places on bones and muscles. It allows bodies to grow larger without collapsing under their own mass. A creature that would struggle to walk on land can glide effortlessly through water. But size also brings power. A larger body can store more energy. It can travel farther without feeding. It can regulate temperature more effectively. It can intimidate predators and overpower prey. In an environment where survival depends on finding food and not becoming food, those advantages add up quickly. As early marine ecosystems became more complex, a kind of evolutionary momentum took hold. Predators grew larger to catch prey. Prey grew larger to avoid being eaten. Over millions of years, this quiet arms race pushed life toward extremes. At the same time, the chemistry of the oceans was changing. One of the most important shifts in Earth's history was the rise of oxygen. Early life had little to no oxygen available, but as photosynthetic organisms spread, oxygen slowly accumulated in the atmosphere and dissolved into the oceans. This change was dramatic. Oxygen allows cells to produce far more energy than they can without it. More energy means faster movement, stronger muscles, and bigger bodies. With more oxygen in the water, animals were no longer limited to small, slow forms. They could grow larger and more active. Muscles could work harder. Nervous systems could become more complex. Predators could chase instead of waiting. And prey had to evolve ways to escape. This is when the oceans began to fill with shapes that feel almost mythical to us today. Imagine swimming through shallow seas where armoured fish the size of cars glide past, their bodies covered in thick bony plates. Picture squid-like creatures with tentacles longer than a human is tall, drifting through dim water with eyes adapted to darkness. Envision sharks not as sleek hunters, but as massive, broad-headed giants capable of swallowing prey whole. These weren't monsters in the sense of horror stories. They were simply animals, shaped by their environment, doing what life always does when given time and resources. They grew. Another factor made this growth possible: stability. For long periods in Earth's past, the climate remained relatively stable for millions of years at a time. Temperatures didn't swing wildly, sea levels stayed high, food chains had time to develop and settle into predictable patterns. In those conditions, large animals thrive. When environments are stable, evolution favours efficiency rather than flexibility. Bigger bodies, slower reproduction, longer lifespans all make sense when the world isn't changing too quickly. And then there's the matter of food itself. Prehistoric oceans were incredibly productive. Microscopic plankton bloomed in vast numbers, fueled by sunlight and nutrients from volcanic activity and erosion. These tiny organisms form the base of enormous food webs. Small animals fed on plankton, larger animals fed on them, and above them all were apex predators that needed enormous amounts of energy to survive. But the ocean could provide it. Even today, the largest animal to ever live, the blue whale, survives entirely on tiny shrimp-like creatures called krill. It grows to lengths greater than any dinosaur, not because it eats large prey, but because it filters massive amounts of small prey every day. This strategy worked just as well, if not better, in ancient seas where plankton blooms could stretch for miles. The water itself also played a role in shaping giant life. Buoyancy reduces the cost of movement. Heat spreads more evenly. Bodies cool and warm slowly. All of this favours size. On land, large animals struggle with heat, weight, and energy demands. In water, those limits are softer, and so, slowly, over hundreds of millions of years, the oceans filled with giants. Some were heavily armoured, built like living tanks. Others were sleek and fast, shaped for pursuit. Some filtered the water peacefully. Others hunted with speed and precision. Each one a product of its time, its environment, and the silent rules of evolution. What's striking is how normal this once was. If you could observe those ancient seas without knowing their age, you might assume that oceans had always been that way. That massive creatures ruling the depths was the natural order of things. In a sense, it was. Only later, much later, did that balance begin to change. But before we get there, it's worth pausing for a moment on something easy to overlook. These giants didn't appear suddenly. There was no single moment when the ocean flipped a switch and decided to grow monsters. It was a gradual process, built from countless small changes layered over time. Each generation slightly larger. Each ecosystem slightly more complex. Each predator pushing its prey to adapt, and each prey species forcing predators to evolve in response. No intention, no design, just the steady pressure of survival playing out over unimaginable spans of time. And through it all, the ocean remained patient. It didn't care about size or dominance. It simply provided the space, the resources, and the rules. Life did the rest. As we move forward, we'll start to look more closely at what those giants actually were. What kinds of creatures filled these ancient seas, how big they truly became, and why, despite all their advantages, most of them are gone now. But for the moment, just let the image settle in your mind. A dark, ancient ocean. Warm currents moving slowly through the depths, light fading as it filters down from the surface, and somewhere in that vastness, a massive shape gliding past, unconcerned, unhurried, perfectly adapted to a world that no longer exists. And in the quiet of that imagined sea, the story continues. Before there were maps, before coastlines had names, before anyone stood at the edge of the water and wondered what lay beyond the horizon, the oceans were already old. Older than forests, older than animals that walked on land, older even than bones. They existed in a world that would feel alien to us now, a planet still learning how to be itself. If you could somehow drift backward through time, past the rise of mammals, past the reign of dinosaurs, past the first insects and plants, you would eventually arrive at an Earth that looked strangely unfinished. The continents would be scattered and bare, their surfaces mostly rock and sand. The sky would carry a different tint, tinted by gases that no longer dominate the air. And the oceans, vast and restless, would cover most of the planet like a single breathing body. There would be no familiar shoreline sounds, no gulls, no waves crashing against piers, no smell of salt carried on the wind. The sea existed, but it had not yet become the place we recognise. It was quieter in some ways, yet far more active in others. Beneath the surface, chemistry ruled everything. The earliest oceans were not blue. They were often greenish, sometimes brown, sometimes tinged with red from dissolved iron. They were rich in minerals carried from volcanic eruptions and underwater vents. These waters were warm, sometimes uncomfortably so, and filled with chemical energy. In many ways, they were less like the oceans we know and more like enormous living laboratories. Life did not begin with fins or teeth or eyes. It began with chemistry finding a way to repeat itself. Simple molecules learned to copy their own structure. Those that did it better lasted longer. Those that failed disappeared. Over time, these molecules formed membranes, then cells, then communities of cells working together. For hundreds of millions of years, life remained small, microscopic, invisible to anything that didn't yet exist to observe it. But even in that simplicity, the foundations of the future were being laid. The ocean was stable in a way land never could be. Temperatures changed slowly. There were no wildfires, no freezing nights, no sudden droughts. Water buffered everything. It softened extremes. It gave life time to experiment, and experiment it did. As more oxygen slowly entered the water, produced by early photosynthetic organisms, the rules of biology began to shift. Oxygen is powerful. It allows cells to extract far more energy from food than anaerobic processes ever could. That energy could be used to grow larger, move faster, and develop more complex structures. This was the quiet beginning of size. At first, the changes were subtle. Slightly thicker cell walls, slightly larger colonies, slightly more complex internal structures. But over immense stretches of time, those small differences accumulated, and eventually the oceans began to host creatures that were no longer invisible. Soft-bodied animals appeared first, strange flat organisms that drifted or clung to the seafloor. Some looked like quilts, others like fronds. Many had no obvious mouths or eyes. They absorbed nutrients directly from the water or filtered particles drifting by. They were not predators. They were simply part of the environment, living where conditions allowed. Then something changed. Predation entered the picture. Once some organisms began feeding on others rather than passively absorbing nutrients, a cascade began. Prey evolved ways to avoid being eaten. Predators evolved ways to catch them. Speed, armor, size, and sensing ability all became valuable traits. The calm balance of early life gave way to competition, and competition favours innovation. The ocean became a place where survival required either hiding well or becoming formidable. Tiny creatures found safety in numbers or in obscurity. Others went in the opposite direction. They grew. In water, growing large is not the burden it is on land. Buoyancy supports weight. Movement can be efficient. A larger body can glide rather than struggle, and a larger animal can dominate territory, control resources, and deter threats simply by existing. Over time, these advantages compounded. The ocean began to fill with shapes that had never existed before. Elongated bodies, muscular tails, hard outer shells, primitive jaws, eyes that could detect motion, nervous systems capable of processing information and coordinating movement. These early seas were not crowded in the way modern oceans are. There was space to grow, to roam, to expand without constant competition from hundreds of similar species. In that openness, size became a strategy that paid off again and again. Temperature played a role as well. Many prehistoric oceans were warmer than today's seas, especially during certain periods. Warmer water holds less oxygen, which might sound like a disadvantage, but it also speeds up metabolic processes. In such environments, organisms that could efficiently extract oxygen and manage energy had an edge. Larger bodies, with more surface area and specialized respiratory structures, could do exactly that. At the same time, the absence of land-based predators meant that the ocean was the primary stage for evolutionary drama. Everything that hunted or was hunted lived in water. The pressure to outcompete neighbours was intense, and so, gradually over millions of years, the ocean became a realm where being small was no longer the safest option. It's important to understand that these changes were not driven by some grand plan. There was no direction, no goal of becoming large or powerful. Evolution simply followed the paths that worked. And in the prehistoric oceans, size worked remarkably well. But the world was still young, and instability was never far away. Volcanic activity regularly reshaped coastlines. Entire seafloors were lifted or submerged. The chemistry of the oceans fluctuated. Oxygen levels rose and fell. Extinction events, some slow and some sudden, erased whole branches of life. Each time this happened, the survivors adapted to the new conditions. Often those survivors were the ones best suited to exploit open niches, and many times that meant growing bigger. By the time complex ecosystems fully established themselves, the stage was set for giants to emerge not as oddities, but as expected outcomes. The ocean had become a place where vastness was not just tolerated, but rewarded. And yet, for all this growth, for all this silent expansion of life beneath the waves, the surface of the planet remained deceptively calm. From above, nothing would have hinted at the drama unfolding below. No splashing whales, no breaching predators, just water, stretching to the horizon. It's strange to think that the greatest creatures Earth would ever know were born in silence, in darkness, under pressure measured in tons, in a world with no witnesses. They did not roar, they did not announce themselves, they simply lived, and in doing so, they shaped the future of life on this planet in ways we are still uncovering. Because as the oceans continued to evolve, and as life continued its slow march toward complexity, the stage was being prepared for something even more remarkable. A time when the sea would not just host large creatures, but true giants. Animals whose size would dwarf almost anything that came before or after. And that story begins when the balance between energy, environment, and evolution tipped just far enough to allow the impossible to become ordinary. That's where we'll drift next, into the conditions that made gigantism not just possible, but inevitable in a world ruled by water and time. When the sea was young, it didn't yet know restraint. It moved with a kind of restless energy, as though still testing its own boundaries, still discovering what it could hold and what it could become. The continents were lower, the shorelines unfamiliar, and beneath the surface the water churned with chemical life in constant motion. This was not the calm, balanced ocean we imagine today. It was an ocean in the middle of becoming something, an environment driven less by stability and more by opportunity. An opportunity, in the language of evolution, often looks a lot like hunger. Hunger is one of the oldest forces in biology. It predates eyes, limbs, and even nervous systems. It is the simple pressure to take in energy before it runs out. In the earliest oceans, that pressure shaped everything. There were no complex food chains yet, no delicate balances, no careful tuning. There was only abundance in some places, scarcity in others, and life constantly responding to both. The sea at this stage was rich in nutrients. Volcanic activity pumped minerals into the water. Rivers carried sediments from newly formed land masses. Sunlight penetrated shallow regions, feeding massive blooms of microscopic life. These microorganisms multiplied rapidly, forming the base of what would become the first true food webs. At first, the energy moved slowly. One cell absorbed another. A colony fed on dissolved compounds, but eventually some organisms developed a more aggressive strategy. Instead of waiting for nutrients to drift by, they began to seek them out. This was the beginning of predation. Once that door opened, it could not be closed again. Because predation changes everything. A predator must be efficient. It must locate food, move toward it, capture it, and process it. Each of those steps rewards certain traits: better movement, faster reactions, stronger structures, more energy storage. And as prey evolved to escape, predators evolved to overcome those defenses. It was in this slow, relentless contest that size began to matter more and more. In a world without land animals, without trees or birds or mammals, the ocean was the only arena where complexity could flourish. There were no boundaries to movement, no cliffs or forests to hide behind. Everything happened in 3 dimensions: up, down, forward, backward. This added an extra layer of challenge and opportunity. A slightly larger body could move more efficiently through water. It could store more energy. It could survive longer without food. It could travel farther in search of prey. Over time, these advantages accumulated, but size alone wasn't enough. The ocean rewarded those who could turn size into power. This is where early marine predators began to change the rules. Some developed hard shells or armor, protecting them from attack and allowing them to push into more dangerous niches. Others evolved grasping appendages capable of seizing prey. Some developed primitive eyes, giving them the ability to detect movement and contrast in the dim underwater light. And as soon as one species gained an advantage, others were forced to respond. The prey that could not outrun or outmaneuver predators either adapted or vanished. Some developed tougher outer layers. Some learned to burrow. Others grew larger themselves, making them harder to subdue. The ocean became an arena of escalation, each adaptation prompting a counter-adaptation in an unending cycle. This is often called an evolutionary arms race, but that phrase can be misleading. It wasn't a sudden sprint toward dominance. It was a slow, grinding pressure, applied over millions of years. Generation by generation, tiny changes stacked on top of one another until the results looked dramatic. And one of those results was size. The young ocean was, in a sense, hungry for energy. It was hungry for complexity. It was hungry for movement. And the organisms that could best exploit those demands tended to grow. Another crucial factor was efficiency. In water, moving a larger body can actually be more efficient than moving a smaller one. A long, streamlined form encounters less resistance per unit of mass. Large animals can glide, coasting on momentum, while smaller animals must constantly expend energy to stay in motion. This is one reason whales today can travel enormous distances while feeding on tiny prey. The physics of water favours scale. In prehistoric oceans, this principle applied just as strongly. Once an organism reached a certain size, the cost of getting bigger often decreased relative to the benefits. Larger lungs or gills meant more oxygen. Larger muscles meant more power. Larger digestive systems meant more efficient processing of food. And unlike on land, there was no gravity-based limit forcing animals to stay small. Water supported their mass. It carried them. It allowed them to exist at sizes that would be impossible in air. But the ocean didn't just reward size, it rewarded timing. Food availability in early seas was not evenly distributed. Nutrient-rich regions formed and disappeared. Currents shifted. Blooms of plankton came and went. Animals that could travel long distances to follow these resources had a major advantage. Larger bodies made this possible. A small creature might thrive in one area but perish when conditions changed. A large creature could migrate, adapt, and endure. Over time, this favoured animals that could cover vast distances, even if slowly. And with migration came another pressure: endurance. Endurance favours efficiency. Efficiency favours size. This feedback loop played out again and again across different lineages. Some became long and serpentine, others bulky and muscular, some relied on speed, others on ambush. But all shared one thing in common. They were pushing the upper limits of what life in water could become. Meanwhile, the chemistry of the oceans continued to evolve. Oxygen levels rose and fell in cycles. Periods of high oxygen allowed for bursts of evolutionary innovation. Periods of low oxygen acted as filters, wiping out species that could not adapt. Each cycle reshaped the biological landscape. Interestingly, many of the largest marine animals appeared during times when oxygen levels were relatively high. This is not a coincidence. Large bodies require efficient oxygen delivery. More oxygen in the water meant more metabolic freedom. More freedom meant more room to grow. Temperature also played a role. Warmer oceans tend to promote faster growth and higher productivity, while colder waters favour slower metabolism and longevity. Over geological time, Earth experienced both conditions, often in alternating phases. During warmer periods, life diversified rapidly. During cooler periods, only the most efficient or adaptable species survived. This pattern helped refine the traits that would later define the ocean's giants. It's worth pausing here to consider something important. None of this happened quickly. We are used to thinking in years or decades. Evolution works in millions of years. The changes that led to giant marine life unfolded so slowly that no single generation ever experienced anything unusual. To them, the world simply was the way it was. And yet, taken together, those tiny changes reshaped the planet. By the time the seas had fully matured, they were no longer quiet or sparse. They were alive with motion. Food webs layered on top of one another. Predators hunted predators. Entire ecosystems existed in the open water, far from any shoreline. The ocean had become a place where being large was not a liability, but a mark of success. But hunger does not stop once it has shaped a system. It pushes further. It drives innovation beyond what seems necessary, and in doing so, it often creates extremes. The hunger of the young ocean did not just produce large animals. It produced some of the largest animals that have ever existed on Earth. Creatures whose size we still struggle to comprehend. Animals that would make modern predators seem modest by comparison. Beings that ruled their environment so completely that nothing could challenge them. And yet their dominance was never guaranteed, because the same forces that allowed giants to rise also carried the seeds of their downfall. As ecosystems grew more complex, they became more fragile. As bodies grew larger, they required more resources. As food webs expanded, they became more sensitive to disruption. The ocean, for all its vastness, was not infinite, and eventually the hunger that drove growth would collide with the limits that could not be ignored. But before that reckoning came, the seas reached a peak unlike anything before or since, a time when massive predators roamed freely, when food chains stretched across entire oceans, and when size itself became a defining feature of life. That era, shaped by hunger and opportunity, set the stage for the true titans of the deep, and it is there, in that age of abundance and escalation, that the story of the greatest ocean giants truly begins. Long before jaws became powerful and bodies stretched into colossal forms, before speed and strength determined survival, something far quieter was reshaping the oceans in ways no creature could sense at the time. It wasn't a predator, it wasn't a climate shift, it wasn't even visible, it was a gas drifting invisibly through water and air, slowly rewriting the rules of life. Oxygen. Today it's easy to take oxygen for granted. Every breath depends on it. Every fire needs it. Every complex organism uses it to release energy stored in food. But for most of Earth's history, oxygen was rare, even dangerous. Early life evolved without it, and in many cases, oxygen was toxic to the organisms that dominated the planet's earliest ecosystems. Then, gradually, almost imperceptibly, that changed. The rise of oxygen began with some of the simplest life forms ever to exist. Tiny, photosynthetic organisms that use sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. At first, that oxygen didn't go far. It reacted with iron in the oceans, turning the water rusty and forming massive deposits that still exist today as banded iron formations. For millions of years, the oxygen was effectively trapped, locked away by chemical reactions, but eventually the sinks filled up. The iron became saturated. The oceans could absorb no more, and slowly, oxygen began to accumulate, first in the water, then in the atmosphere. This moment, often called the Great Oxidation Event, changed everything. Oxygen is incredibly efficient at helping cells extract energy from food. Compared to anaerobic metabolism, which doesn't use oxygen, aerobic metabolism can produce many times more energy from the same amount of fuel. This meant organisms that could tolerate and use oxygen suddenly had access to an enormous energetic advantage. More energy meant more possibilities. Cells could afford to be larger. They could maintain more complex internal structures. They could move faster, react quicker, and sustain activity for longer periods. Evolution, which had been constrained by tight energy budgets for billions of years, suddenly had room to experiment. In the oceans, this change was profound. Animals that had once been limited to soft bodies and slow movements began to develop muscle tissue capable of sustained motion. Nervous systems became more sophisticated, allowing for faster responses and better coordination. Sensory organs improved. Vision emerged not as a luxury, but as a necessity in an increasingly competitive environment. And as these changes accumulated, something remarkable happened. Life started to scale up. With oxygen flowing more freely, the limitations that had kept organisms small began to loosen. Larger bodies could be maintained. Larger muscles could function without exhausting their energy supply. Larger brains could be supported. The ceiling that had capped biological ambition was lifted. But oxygen didn't just make larger animals possible, it made them practical. In low oxygen environments, being large is a disadvantage. Oxygen has to diffuse into tissues, and the bigger the body, the harder it is to deliver enough of it to every cell. But with higher oxygen levels, diffusion becomes easier, circulation becomes more effective, and the entire system becomes more resilient. This is why periods of high atmospheric oxygen in Earth's history often coincide with episodes of gigantism. On land, it led to enormous insects. In the sea, it opened the door for creatures of staggering size. At the same time, oxygen reshaped food webs. More oxygen meant more active predators. More active predators meant prey had to evolve better defenses or escape strategies. Speed increased, armor thickened, senses sharpened, and in many cases size became the simplest solution. A larger animal could avoid being eaten simply by being too big to handle. It could travel farther to find food. It could dominate territory. It could afford to be slower, because fewer things could threaten it. This didn't mean every large animal was a predator. Some became filter feeders, cruising through nutrient-rich waters and consuming enormous quantities of tiny organisms. Others became opportunistic hunters, relying on strength rather than speed. But in nearly every case, oxygen made their existence possible. It also changed how long animals could live. With more efficient energy use came longer lifespans. Longer lifespans allowed for slower growth, larger final sizes and more stable populations. This stability encouraged the development of complex behaviours and long-term survival strategies. The ocean, once dominated by simple life forms, began to resemble something closer to an ecosystem as we understand it today. Relationships formed, niches stabilised, balance emerged, though it was always temporary, and all of this rested on the quiet presence of oxygen. It's worth pausing here to appreciate how subtle this transformation was. There was no single moment when the ocean suddenly filled with giants. No dramatic turning point visible to any living thing at the time, just a slow, steady increase in a gas that altered what life could afford to be. The creatures themselves had no awareness of this shift. They did not evolve to be large because oxygen was rising. They evolved because those individuals that could take advantage of the new conditions survived better than those who could not. Evolution has no foresight. It only has momentum. As oxygen levels continued to fluctuate, periods of abundance alternated with periods of scarcity. During oxygen-rich phases, life flourished and grew larger. During declines, many species vanished, unable to cope with the reduced energy supply. These cycles acted as filters, refining life again and again. Each time oxygen rose, the survivors pushed boundaries a little further. Another important effect of oxygen was its influence on temperature and climate. Oxygen allowed for the development of ozone in the upper atmosphere, which shielded the surface from harmful ultraviolet radiation. This protection stabilized surface environments and allowed life to expand into new zones, including shallower waters and coastal regions. More stable environments meant more predictable ecosystems. More predictability allowed for specialization. And specialization, over time, leads to complexity. In the sea, complexity often translates into size. Consider how food moves through an ecosystem. Energy begins with microscopic producers, passes to small consumers, then to larger predators. At each step, energy is lost. Only a fraction moves upward. For a large predator to exist, the system below it must be extremely productive. Oxygen made that productivity possible. With abundant oxygen, plankton blooms became more intense. More plankton meant more food for small animals. More small animals meant more food for larger ones. The pyramid grew taller. Eventually, the ocean could support creatures that required enormous amounts of energy just to survive. This is how the groundwork was laid for some of the most massive animals in Earth's history. Not overnight, not suddenly, but inevitably. The ocean became a place where energy flowed freely enough to support giants, and once that threshold was crossed, evolution took full advantage of it. Yet there was a limit, even here. Because oxygen, for all its benefits, is also reactive. It accelerates decay, it fuels fires, it can damage cells if not carefully regulated. Life had to evolve complex systems to manage it, to use it without being destroyed by it. Those systems took time to develop, and only the organisms that struck the right balance survived long enough to grow truly large. This balance between energy and stability, between abundance and control, shaped every giant that followed. And it's why the rise of oxygen stands as one of the most important turning points in the history of life. Without it, the oceans would have remained filled with small, simple organisms. With it, they became the stage for some of the most awe-inspiring creatures to ever exist. Creatures that would soon test the limits of size, strength, and survival. Because once oxygen had done its work, once the sea had the energy it needed, evolution began asking a new question. Not whether life could grow bigger, but how big it could become before the ocean itself pushed back. Water changes everything. It changes how things move, how they grow, how they rest, and how they survive. It bends the rules that govern life on land and replaces them with a different set of constraints, ones that are quieter but far more forgiving when it comes to size. To understand why prehistoric oceans could support giants, you have to understand what water does to weight, and why that single factor reshaped the possibilities of life more than almost anything else. On land, gravity is relentless. Every kilogram of mass must be supported by bone, muscle, and connective tissue. As an animal grows larger, its volume increases faster than the surface area of its limbs. This means that strength does not scale evenly with size. A creature twice as large is not twice as strong. It is many times heavier, and its skeleton must bear that burden at all times. That's why land animals hit hard limits. Even the largest dinosaurs were pushing the edge of what was physically possible. Their bones had to be massive, their movements slow and deliberate, their bodies carefully balanced to avoid collapse. Every step carried risk. Every injury was potentially fatal. Water changes that equation completely. In water, weight is not something an animal must constantly fight. Buoyancy offsets mass. The surrounding fluid supports the body, reducing the strain on bones and muscles. A creature that would be crushed under its own weight on land can float, move, and maneuver with relative ease in the ocean. This is why the largest animal that has ever lived does not walk on land. It swims. The blue whale, heavier than any dinosaur, exists comfortably in water because the ocean carries most of its weight. Its skeleton does not need to be massively overbuilt. Its muscles do not need to constantly fight gravity. Its sheer size becomes an advantage rather than a liability. This principle applied just as strongly in prehistoric seas. As life grew larger, the ocean made that growth sustainable. It allowed bodies to expand without collapsing. It allowed muscles to power motion without constant strain. It allowed organisms to grow to sizes that would be completely impossible in air. But buoyancy is only part of the story. Water also changes how energy is spent. On land, movement is costly. Lifting limbs, pushing against gravity, maintaining posture all require constant energy input. In water, movement is smoother and more continuous. Once an animal is in motion, it can glide. Momentum carries it forward. Large bodies, in particular, benefit from this. They lose energy more slowly and maintain speed more efficiently. This is why large marine animals often appear to move with such calm, deliberate grace. Their size works with the water, not against it. In prehistoric oceans, this meant that being large could actually reduce the energy cost of travelling long distances. A massive predator could patrol vast areas without expending excessive energy, while smaller animals had to work harder just to keep up. That advantage compounded over time. Large animals could follow food sources as they shifted. They could migrate when conditions changed. They could survive longer periods without eating. And in an environment where food availability was not always predictable, that resilience mattered. Another key factor was stability. Water buffers temperature changes far more effectively than air. It warms and cools slowly. This creates a more stable environment, especially in deeper regions of the ocean. For large animals, stability is critical. Big bodies take longer to heat up and cool down. Sudden temperature shifts can be dangerous. The ocean smoothed out those fluctuations. It provided a thermal cushion that made large size safer and more sustainable. This allowed animals to evolve longer lifespans, slower metabolisms, and larger overall body plans. And with longer lives came new evolutionary strategies. Large animals could afford to grow slowly. They could invest in durability rather than speed. They could mature over years instead of months. This led to the emergence of creatures that were not just big, but also long-lived and stable within their ecosystems. Weight in water also behaves differently when it comes to feeding. On land, supporting a large head or massive jaws is costly. The neck must bear the load. Muscles must constantly work to keep everything upright. In water, the head floats. Even enormous jaws can be supported with minimal effort. This allowed marine predators to evolve huge mouths, powerful biting mechanisms, and expansive feeding strategies. Some could swallow prey whole. Others could filter massive volumes of water. Others still developed crushing bites capable of breaking shells and bone. These feeding strategies would be impractical or impossible on land at comparable sizes. Water also allows for a different kind of speed. On land, speed requires rapid leg movement and precise coordination. In water, speed can be achieved through streamlined shapes and powerful tail strokes. Larger bodies can generate more thrust with each movement, making them surprisingly fast despite their size. This meant that becoming larger did not necessarily mean becoming slower. In many cases, the opposite was true. Large marine predators could be both massive and agile, a combination rarely seen on land. The result was a world where size became a dominant strategy. Small animals still existed, of course. They filled niches that large ones could not. But the upper limits kept expanding. Each evolutionary success paved the way for something even larger. There was also safety in size. In an environment full of predators, being too big to eat is a powerful advantage. Once an animal reaches a certain threshold, very few threats remain. This reduces selective pressure to remain small and agile. Instead, selection favours continued growth. Thicker tissues, stronger defences. This is one reason why many prehistoric marine animals appear to have grown continuously throughout their lives. Unlike most land animals, which stop growing once they reach maturity, many aquatic species never truly stop. They grow as long as resources allow. And the ocean, for long periods, provided abundant resources. Another often overlooked factor is pressure. As depth increases, pressure rises dramatically. Many large marine animals live not just near the surface, but in deeper waters where pressure is intense. Smaller, more fragile bodies struggle under such conditions. Larger bodies, with more mass and internal support, can better withstand pressure differences. This allowed large animals to exploit deeper habitats, accessing food sources unavailable to smaller competitors. It also reduced competition, further favouring size. Over millions of years, these advantages reinforced one another. Buoyancy reduced the cost of weight. Stability supported large bodies. Efficient movement conserved energy. Abundant food fueled growth. Pressure tolerance opened new habitats. Longevity increased reproductive success. Together, they created a feedback loop that steadily pushed life toward gigantism. It's important to understand that this was not a single event or a sudden explosion of size. It was a gradual trend, playing out across countless species and time periods. Some lineages grew large and vanished. Others shrank or adapted in different ways. But the overall direction was clear. The ocean made size viable, and once size became viable, evolution explored it thoroughly. This is why, when we look back at prehistoric seas, we don't just see one or two large creatures. We see entire communities shaped around scale. Large predators, large prey, large filter feeders. Entire ecosystems operating at a scale that feels almost unreal by modern standards. It also explains why similar patterns emerged again and again across different eras. Whenever conditions allowed, life in the ocean tended to grow large. When conditions worsened, size became a liability, and smaller forms prevailed. The rule of water and weight never changed. Only the environment around it did. And this rule still applies today. Modern oceans still favour large animals. Whales, sharks, and giant squid are not evolutionary flukes. They are the continuation of a pattern that began hundreds of millions of years ago. They exist because water allows them to exist. But as stable as the ocean can be, it is not immune to change. The same forces that once enabled giants would eventually begin to limit them. Shifts in climate, oxygen levels, and food availability would alter the balance. The ocean would no longer be the endlessly accommodating environment it once was. And when that happened, size would become a vulnerability instead of a strength. But before that turning point arrived, the seas reached their most extreme expression of life at scale, a time when predators grew to lengths that defy intuition, when food chains stretched across entire basins, and when being enormous was not an exception, but an expectation. That era, shaped by water and weight, was unlike anything before or since, and it was only just beginning. As the oceans deepened and spread, as continents shifted and climates settled into long rhythms, another quiet force began to shape life beneath the surface. It wasn't dramatic or sudden. It didn't announce itself with catastrophe or spectacle. It arrived gradually, almost unnoticed, and yet it would influence the size, behaviour and fate of marine life for hundreds of millions of years. That force was cold. Not the biting cold of ice sheets or frozen seas, but the steady, persistent chill of deep water. The kind of cold that seeps in slowly, that never truly leaves, that wraps the deep ocean in a kind of timeless stillness. As the surface waters of the planet warmed and cooled with the turning of eras, the depths remained largely unchanged, dark, cold, and remarkably stable. This stability mattered more than it might seem. In shallow waters, conditions are in constant flux. Temperatures rise and fall with the seasons. Storms churn the water. Sunlight comes and goes. Food availability can change quickly. Life in these regions must be flexible, fast-growing, and quick to reproduce. There is little room for slow development or long-term planning. But in the deep ocean, everything moves differently. Temperature changes are minimal. Light barely penetrates. Currents move slowly. Food arrives not in sudden abundance, but as a steady rain of organic matter drifting down from above. In this environment, speed is less important than efficiency. Patience becomes an advantage, and longevity becomes possible. Cold water slows biological processes. Chemical reactions occur more slowly. Metabolisms tick along at a reduced pace. Growth takes longer, but so does aging. A creature living in cold depths does not burn through energy quickly. It can afford to live slowly. And slow life, paradoxically, allows for great size. When metabolism is low, an animal does not need to eat constantly. It can survive on infrequent meals. It can grow gradually over many years, sometimes decades or centuries. Each small increase in size adds to its advantage without dramatically increasing its energy demands. This is one reason why some of the largest animals in the ocean today are associated with colder waters. Whales migrate through cold currents. Giant squid dwell in deep, frigid zones. Even massive sharks often prefer cooler regions. The same pattern existed in prehistoric seas, only on a much grander scale. As marine life spread into deeper waters, it encountered an environment that rewarded patience over speed. Animals that could tolerate cold and operate efficiently at low metabolic rates had access to vast, underutilized spaces. There was less competition, fewer predators, more room to grow, and because deep water offered protection from surface disturbances, these animals could persist for long periods without drastic environmental pressure. Longevity followed naturally. Long-lived animals have more time to grow. They can reach sizes impossible for short-lived species. They can afford slower reproductive cycles. They can invest energy into maintenance and repair rather than rapid turnover. Over evolutionary time, this creates a bias toward large, durable forms. The cold depths also change the relationship between predator and prey. In warm, shallow waters, predator-prey interactions are fast and chaotic. Chases are short. Reactions are immediate. In deep water, encounters are rarer and more deliberate. A predator may go long periods without feeding. When it does find prey, success matters. This favours animals that can store energy efficiently and survive long intervals between meals. Larger bodies do exactly that. They act as reservoirs, smoothing out the unpredictability of food availability. It also favours ambush strategies over pursuit. Instead of chasing prey, many deep-sea predators rely on stealth, patience, and sudden bursts of movement. This again favours size, because a large body can generate tremendous power in short moments without needing constant activity. Cold water also holds more dissolved oxygen than warm water. While cold slows metabolism, it also ensures that oxygen remains available, even at depth. This creates a unique balance: slow energy use paired with reliable oxygen supply. This balance is ideal for large animals. They can afford to grow slowly. They can afford to be heavy. They can afford to invest in thick tissues and long lifespans. The environment supports it. Over time, this led to the emergence of a very different kind of oceanic life than what existed near the surface. Not frantic or fast, but massive, deliberate, and enduring. Some of the largest prehistoric marine animals are believed to have spent much of their time in deeper, cooler waters, rising toward the surface only to feed or reproduce. Their size was not just a result of abundance, but of restraint. They did not need to burn energy quickly. They did not need to compete constantly. They simply endured. There is also a structural advantage to cold environments when it comes to size. Cooler temperatures allow tissues to remain firm and resilient. Proteins are more stable. Cellular processes are less prone to rapid degradation. This reduces wear and tear over time. In warm environments, cells divide more rapidly, but they also accumulate damage more quickly. In cold environments, everything slows down, including aging. This helps explain why some marine species today exhibit remarkable longevity. Greenland sharks, for example, can live for centuries. Deep-sea corals can be thousands of years old. These are not anomalies. They are products of the same principles that once allowed prehistoric giants to thrive. Another factor often overlooked is noise. The deep ocean is quiet, not silent, but subdued. Sound travels far, but activity is sparse. There is no constant motion, no visual clutter, no chaotic swarm of life. In such an environment, large animals can move without drawing attention. Their size does not betray them as easily as it would in a crowded reef. This subtlety allowed large predators to exist without constant conflict. They did not need to fight frequently. They did not need to defend territory aggressively. They could exist in relative isolation, moving slowly through enormous ranges. All of this contributed to a world where life unfolded at a different pace. Time itself seemed to stretch in the deep. Generations passed slowly. Changes accumulated gradually. Evolution worked with long brushstrokes rather than sharp lines. And in that slow, patient environment, gigantism flourished. It's important to remember that these giants were not aberrations. They were not mistakes or curiosities. They were the logical outcome of a system that rewarded efficiency, endurance, and scale. The cold depths did not create monsters. They created specialists. Creatures adapted to a world where speed mattered less than persistence, where survival depended on patience rather than aggression, where size was not a burden but a form of insurance. And yet, this way of life came with a hidden vulnerability. When conditions change slowly, species adapt slowly. When food webs shift gradually, populations can adjust. But when change happens quickly, when temperatures rise, currents shift, or oxygen levels drop, large, slow-growing animals struggle to respond. Their very strengths become weaknesses. A small animal can adapt or reproduce quickly. A giant cannot. A slow metabolism cannot suddenly speed up. A long lifespan cannot be shortened to match rapid environmental change. And so, while the cold depths once offered refuge and opportunity, they also set the stage for future fragility. But that reckoning was still far away. For now, the oceans remained vast, cool and accommodating. Life continued to explore the limits of form and function. Giants moved through the darkness with unhurried confidence. Food chains stretched long and deep. The balance held. And as the seas continued to change, as continents shifted and climates evolved, another powerful force began to shape the destiny of ocean life. A force that would turn size into both an advantage and a risk. Because in a world governed by slow lives and cold depths, even small shifts can echo for millions of years. Beneath the surface of the ancient oceans, long before anything walked on land, a quiet contest was unfolding. It didn't involve strategy in the way humans think of it, nor intentional planning. It was a contest written into biology itself, driven by survival, repeated endlessly across generations. It was an arms race, not of weapons or nations, but of bodies, senses and instincts. And over time, it shaped the sea into a place where size, power and precision became inseparable. At first, life in the ocean had little need for conflict. Early organisms absorbed nutrients passively. They drifted, filtered and divided. There was no pursuit, no chase, no evasion. But once predation emerged, once some organisms began feeding on others, everything changed. Predation creates pressure. Pressure creates response. And response, over time, becomes evolution. The earliest predators were simple. They engulfed smaller organisms or absorbed them through membranes. But as prey became more numerous and more varied, predators had to improve. And as predators improved, prey had to do the same. This back and forth escalated slowly, relentlessly, over millions of years. One of the first major changes was movement. Being able to move with intention was a profound advantage. It allowed predators to seek out food rather than waiting for it. It allowed prey to flee instead of hoping to be overlooked. Once movement became common, speed and control became valuable traits. From there, specialization followed. Some organisms evolved streamlined bodies for pursuit. Others developed hard outer shells for defense. Some grew spines. Some learned to burrow. Others developed early sensory systems to detect changes in water pressure or chemical traces left by other organisms. Each adaptation forced a response. If prey grew harder to bite, predators developed stronger jaws. If prey became faster, predators became more agile. If prey learned to hide, predators evolved better senses. The ocean became a place of constant adjustment, a living feedback loop where every advantage was temporary. And in this competition, size emerged as one of the most powerful tools available. Being larger offered several advantages at once. It reduced the number of potential predators. It allowed greater strength. It enabled longer pursuits. It provided more space for muscle, organs, and energy storage. In many cases, it removed the need to flee at all. For predators, size meant dominance. For prey, it meant safety. This led to an interesting pattern. Some lineages grew larger to become predators. Others grew larger simply to avoid being eaten. Both strategies reinforced one another. As prey species increased in size, predators had to follow or risk starvation. As predators grew larger, prey had to grow larger still, or develop new defences. The result was a steady upward pressure on body size across entire ecosystems. This is the essence of the arms race beneath the waves. But unlike human arms races, this one had no finish line. There was no ultimate weapon, no final advantage. Every solution created a new problem. Every gain demanded a counter. Over time, this process produced extraordinary diversity. Some predators evolved massive jaws lined with serrated teeth, capable of tearing through thick flesh. Others developed crushing plates designed to break shells. Some used suction to pull prey in before it could react. Others relied on ambush, lying still for long periods before striking with explosive force. Prey, meanwhile, developed armor, spines, toxins, camouflage, and complex behaviors. Some became flat and buried themselves in sediment. Others grew thick scales. Some evolved schooling behavior, confusing predators through sheer numbers. And through all of this, size continued to increase. One reason size was such an effective strategy is that it simplified the equation of survival. A large animal does not need to be fast if nothing can catch it. It does not need to hide if nothing can harm it. It does not need to reproduce rapidly if it lives long enough to reproduce many times. This made large size a kind of evolutionary shortcut. But it also created dependencies. Large predators required large prey or abundant smaller prey. Large prey required stable environments with consistent resources. This tied entire ecosystems together in delicate ways. When one part shifted, everything else felt the effects. As oceans became more complex, food webs lengthened. Energy passed through multiple levels before reaching the top. This made ecosystems productive, but also fragile. Still, during long stretches of Earth's history, the balance held. Some of the most impressive marine predators evolved during these times, creatures with bodies shaped like torpedoes, built for sustained swimming, animals with jaws powerful enough to crush bone, hunters that ruled their domains with little competition. At the same time, prey species reached extraordinary sizes as well, not to hunt, but to survive. Thick-bodied animals that relied on mass alone for defense. Slow-moving giants that few predators could challenge. This created a strange equilibrium where both hunter and hunted could be enormous. It's important to understand that this was not chaos, it was structure. The arms race did not produce random results. It followed patterns governed by physics, energy, and environment. In water, movement costs energy. Energy must come from food. Food availability limits population size. Population size limits how many large animals an ecosystem can support. As long as these factors remained in balance, the system could sustain giants. And for millions of years, it did. Another important factor was competition within species. As animals grew larger, competition shifted from survival to dominance. Individuals competed for mates, territory, and access to resources. Larger size often meant greater reproductive success. This reinforced the trend toward gigantism even further. At the same time, sensory systems became more refined. Eyes grew larger and more complex. Lateral lines allowed animals to sense vibrations. Chemical receptors detected traces of prey or predators from great distances. This sensory arms race made the ocean a far more dynamic place. Nothing moved unnoticed. Nothing acted without consequence. And yet, for all this activity, the deep ocean remained calm on the surface. These struggles played out silently, unseen, in a world without witnesses. One of the most fascinating outcomes of this arms race was convergence. Unrelated species, separated by millions of years, evolved similar shapes and strategies. Streamlined bodies appeared again and again. Powerful tails re-emerged in different lineages. Large jaws evolved independently in multiple groups. This tells us something important. The ocean imposes rules, and when life plays by those rules long enough, it often arrives at similar solutions. The arms race beneath the waves did not produce chaos, it produced order. A harsh, unforgiving order, but one that worked. Yet, even as this evolutionary contest intensified, it remained constrained by the environment. There were limits to how much food could be produced, limits to how much oxygen could be used, limits to how large a body could grow before the costs outweighed the benefits. Those limits were not fixed. They shifted with climate, chemistry, and geology. When conditions were favourable, size increased. When conditions worsened, size became a liability. This is why the fossil record shows waves of gigantism followed by decline. The arms race would escalate, reach a peak, then collapse under its own weight when resources changed. Then, slowly, the cycle would begin again with new players. What makes this process so remarkable is its persistence. For hundreds of millions of years, across multiple mass extinctions, across changing continents and climates, the same pattern re-emerged. Life would recover, predation would return, size would increase, the ocean would once again fill with giants. This suggests that gigantism in the sea is not an anomaly. It is a natural consequence of how life behaves in water under the right conditions. The arms race beneath the waves was not driven by ambition or aggression. It was driven by simple rules. eat or be eaten, adapt or disappear, grow or fall behind. And in that relentless logic, size became one of the most powerful tools available. But as with all arms races, escalation comes at a cost. The more specialized an organism becomes, the less flexible it is. The more energy it requires, the more vulnerable it becomes to change. The more it depends on a stable environment, the more it suffers when that stability is lost. And slowly, imperceptibly, the oceans were moving toward a point where the rules would shift again. The giants would not vanish overnight. They would persist for millions of years more. But the conditions that allowed them to dominate were already beginning to change. Currents would shift. Climates would cool and warm. Food webs would reorganize. Oxygen levels would fluctuate. The arms race beneath the waves had produced some of the most extraordinary creatures to ever live, but it had also made the ocean a place where balance was everything. And balance, as Earth's history shows again and again, never lasts forever. There was a time in the history of the oceans when size was not merely an advantage, not merely one trait among many, but the defining factor between survival and disappearance. It was a period shaped by pressure, abundance, and competition so intense that the line between living and vanishing often came down to one simple reality. Bigger bodies endured longer. This was not because the ocean favoured size in some abstract way. It was because the conditions of the world slowly and steadily made size the safest place to be. By this point in Earth's history, the seas were no longer experimental playgrounds of early life. They had matured into complex layered ecosystems, food webs stretched from microscopic plankton all the way up to massive predators. Energy flowed upward through these layers, and every step in that chain introduced risk. The further up an organism sat, the more energy it required, and the fewer mistakes it could afford to make. And yet, again and again, evolution pushed life upward anyway. The reason lies in how danger operated in the prehistoric ocean. For small creatures, danger was constant. A slightly larger fish, a sudden change in current, a shadow passing overhead could mean the end. Small bodies offered little margin for error. A single injury, a missed feeding opportunity, or a brief change in conditions could be fatal. Larger bodies, by contrast, absorbed risk more easily. A large animal could miss a meal and survive. It could sustain minor injuries. It could travel long distances in search of food. It could endure fluctuations in temperature or oxygen that would kill smaller organisms outright. Size became a buffer against uncertainty. This buffering effect mattered more and more as ecosystems grew crowded. As biodiversity increased, competition intensified. More species meant more mouths to feed, more competition for space, and more interactions between predators and prey. In such environments, being average was dangerous. You were neither fast enough to escape nor large enough to intimidate. Size, however, offered clarity. A sufficiently large animal occupied a different tier of the ecosystem. It was not just another competitor. It was a presence. Its very existence reshaped the behavior of other species. Smaller animals avoided it. Medium-sized predators learned to keep their distance. Entire food webs adjusted around it. In this way, size became a form of ecological authority. But authority came with responsibility, at least in evolutionary terms. A large body demands more energy. It requires reliable access to food. It cannot survive on chance encounters alone. This meant that only environments with consistent productivity could support truly large animals. For long stretches of Earth's history, the oceans provided exactly that. Nutrient cycles stabilized. Plankton populations flourished. Ocean currents distributed food across vast regions. Seasonal changes occurred, but they were predictable. The ocean became, in effect, a slow-moving conveyor belt of energy. In such a system, large animals had the advantage. They could migrate to follow food. They could dive to different depths to exploit different resources. They could shift their behavior in subtle ways without needing to evolve entirely new forms. This flexibility made size not just viable, but optimal. Another factor that made size synonymous with survival was reproduction. Large animals often reproduce more slowly, but they also tend to produce offspring with higher survival rates. Their young are larger, stronger, and more developed at birth. They require less immediate protection and are better equipped to navigate their environment. Over time, this leads to more stable populations. While small species may boom and crash rapidly, large species tend to persist, weathering environmental fluctuations that wipe out more fragile organisms. This persistence reinforces the trend towards size. Species that survive long enough continue to shape ecosystems, influencing which traits are favoured in others. And then there is the matter of fear. Fear is not just an emotion. In evolutionary terms, it is a force. Prey species evolve behaviours and morphologies in response to predators. When predators are large, fear scales accordingly. The presence of enormous hunters changes how entire communities behave. Smaller animals alter their feeding times. They stick closer to shelter. They evolve group behaviours. They sacrifice efficiency for safety. This creates an environment where only the largest predators can operate freely. Everything else must adapt around them. Over millions of years, this dynamic creates a feedback loop. Large predators encourage prey to grow larger. Larger prey encourage predators to grow larger still. Each generation pushes the boundary a little further. It's important to understand that this did not happen uniformly. Some lineages embraced size, others found different strategies. But whenever conditions allowed, size emerged as one of the most reliable solutions to the problem of survival. Even extinction events, which periodically reset ecosystems, often reinforce this pattern. After mass extinctions, ecosystems are simplified. Many species vanish. Food webs collapse and then slowly rebuild. In these recovery phases, organisms that can grow large and exploit broad ecological niches often gain an advantage. They face less competition and can expand rapidly. This pattern repeated again and again throughout geological time. In the wake of devastation, the ocean would quiet. Then gradually life would return. Small species would appear first, then medium-sized ones, and eventually, once stability returned, the giants would follow. It's tempting to imagine that gigantism is a fluke, something that happened once or twice. But the fossil record tells a different story. It shows repeated waves of large marine animals emerging, dominating, and then fading, only to be replaced by new giants shaped by the same underlying forces. Size, in this context, was not an accident. It was a solution, but it was also a gamble. Large animals require time to grow, time to reproduce, time to adapt. When environmental conditions change rapidly, that time becomes a liability. Smaller species can adapt in a few generations, giants cannot. This tension sat quietly beneath the surface during the ages when size meant survival. The oceans appeared stable, but they were never static. Currents shifted, climates warmed and cooled, chemistry changed. Continental positions altered ocean circulation. As long as these changes were slow, giants thrived. But when changes accelerated, the balance began to tip. Still, during the height of this era, the ocean belonged to the large. Massive predators cruised open waters. Enormous filter feeders strained plankton from nutrient-rich currents. Armoured beasts moved slowly across ancient seafloors. The scale of life reached heights that would never again be matched in quite the same way. And for a time, this worked. The oceans were vast enough to support it. The food webs were deep enough to sustain it. The climate was stable enough to allow it. Size meant survival because survival demanded size. But beneath that apparent stability, forces were gathering. Subtle changes in temperature, shifts in ocean chemistry, alterations in circulation patterns. None of them dramatic on their own, but together they began to reshape the environment that had made gigantism possible. The ocean was preparing to change again, and when it did, the very trait that had once guaranteed survival would become a liability that no amount of strength could overcome. But that reckoning lay ahead. For now, the seas still belonged to the giants, and the slow, deliberate rhythm of their lives continued, unchallenged, in a world where being large was the safest way to exist. There came a time when the oceans reached a kind of peak, a long, drawn-out moment in Earth's history when everything that had been building quietly for hundreds of millions of years finally converged. The chemistry was right. The temperatures were stable enough. Oxygen was abundant. Food webs were deep and productive. The seas had become vast highways of energy and motion. And in those waters, the largest animals the planet had ever known rose to dominance. This was the age of the ocean titans. It did not begin with a single species or a single moment. It unfolded gradually as evolutionary pressures aligned and the rules of survival favoured scale above all else. Over time, the oceans filled with creatures that dwarfed anything that had come before them, animals so large that even now, long after they vanished, their remains seem almost unreal. These were not monsters in the dramatic sense. They were not aberrations or accidents. They were the natural result of a world that for a while made immense size not only possible but practical. In these ancient seas, predators reached lengths measured in tens of meters. Some were built like living torpedoes, sleek and powerful, capable of covering enormous distances with minimal effort. Others were bulkier, designed to dominate through mass rather than speed. Some hunted actively, others ambushed, and still others filtered the water itself, feeding on swarms of smaller life that drifted endlessly through the currents. The oceans had become layered environments, with different giants occupying different levels. Near the surface, massive hunters patrolled warm waters, following migratory prey. In mid-depths, long-bodied predators cruised the twilight zone, their senses tuned to faint vibrations and subtle changes in pressure. Below them, in darker waters, even larger forms moved slowly, their metabolism low, their movements deliberate. What united them was scale. These animals were not simply larger versions of smaller creatures. They were built differently. Their skeletons were reinforced, their muscles arranged for endurance rather than speed. Their circulatory systems were optimized to deliver oxygen across vast bodies. Their jaws and teeth were designed for efficiency, not waste. Some had skulls larger than modern cars. Some had teeth the size of knives. Others had no teeth at all, relying instead on massive mouths and filtering structures to harvest microscopic life by the ton. The variety was astonishing, and yet, despite their differences, they shared a common advantage: dominance through presence. In ecosystems dominated by giants, behaviour changes. Smaller animals adapt their lives around the movements of larger ones. Feeding times shift, migration routes adjust. Entire communities organise themselves to avoid or exploit the patterns of the largest creatures. This kind of ecological influence is difficult to overstate. A single large predator can shape the distribution of hundreds of species. Multiply that by dozens of giant species, and the entire ocean becomes structured around their existence. In these ancient seas, giants were not just participants, they were architects. Their movements stirred nutrients from the depths, their waste fertilised plankton blooms, their feeding patterns controlled population sizes, even their deaths reshaped environments, providing massive influxes of energy to deep-sea ecosystems. When one of these titans died, it did not simply disappear. Its body became a temporary ecosystem, supporting scavengers, bacteria, and specialised organisms for years. Entire food chains sprang up around these fallen giants, just as they do today around whale falls. The ocean, in a sense, recycled its giants. What made this era particularly remarkable was how long it lasted. Unlike brief evolutionary experiments, the age of ocean titans spanned tens of millions of years. Different groups rose and fell, but the overall pattern remained consistent. When one lineage declined, another took its place. The role of largest animal in the sea passed from one form to another, but it was never vacant for long. This persistence suggests that the environment itself favoured such creatures, and indeed, during this time, global conditions were unusually stable. Sea levels were high. Continental configurations allowed for wide, uninterrupted oceans. Currents distributed nutrients efficiently. Climate fluctuations occurred slowly enough for life to adapt. The result was a long equilibrium where gigantism could flourish. It's also important to understand that these giants did not exist in isolation. They were part of intricate ecosystems that included countless smaller species. Reef systems flourished. Shoals of fish moved in immense numbers. Invertebrates filled every available niche. The giants depended on this diversity as much as it depended on them. Energy flowed upward through these systems in vast quantities. Plankton fed small fish fed larger ones fed the giants. Each step involved losses, but the overall productivity of the ocean was high enough to sustain the entire structure. This is why such giants are rare today. Modern oceans, while still productive, are less uniformly rich than their prehistoric counterparts. Changes in circulation, climate, and nutrient flow have made it harder for such massive energy pyramids to exist. But in the age of the ocean titans, those conditions were in place. The seas were, in a sense, overflowing, and because of that abundance, evolution was free to explore extremes. Some titans specialized in speed, using long, streamlined bodies to chase down prey over open water. Others specialized in strength, developing crushing jaws capable of breaking bone and armor. Some specialized in efficiency, filtering enormous volumes of water to extract tiny organisms. All of them, in their own way, represented the outer edge of what life could achieve in water. There is something important to understand about this period, something that often gets lost when we think about prehistoric giants. They were not clumsy or slow by default. While their size might suggest sluggishness, many were highly adapted, agile in their own environments, and capable of surprising bursts of speed. Their movements were economical, refined by millions of years of selection. They did not waste energy. They didn't need to. They lived in a world that rewarded patience and scale, and yet, even at the height of their dominance, the seeds of change were already present. The same interconnectedness that made these ecosystems so productive also made them sensitive. A shift in temperature could affect plankton. A change in currents could alter food distribution. A drop in oxygen could ripple upward through the food chain. The larger the animal, the more exposed it was to these changes. Still, during this long chapter of Earth's history, those shifts were slow enough that the giants endured. They adapted gradually. They migrated. They adjusted their diets. They persisted. The ocean, for a time, belonged to them. It is difficult for us, living in a world where most animals are relatively small, to truly grasp what this meant. To imagine seas where creatures longer than buildings move through open water as a normal part of life, where shadows beneath the surface signal not just large animals but colossal ones. And yet this was once reality. A reality shaped by physics, chemistry, and time. A reality in which size was not exceptional, but expected. The Age of the Ocean Titans stands as one of the most extraordinary chapters in the history of life. It represents a moment when the planet's systems aligned just right to allow biology to reach its maximum scale. But as with all such moments, it was temporary. The ocean would not remain unchanged forever. Forces beyond the control of any organism were already in motion. Currents would shift, climates would fluctuate, chemistry would alter, and the delicate balance that sustained the giants would begin to strain. For now, though, in this long, quiet era, the giants ruled unchallenged. They moved through the depths with unhurried confidence, unaware that the very conditions that allowed their existence were slowly, almost imperceptibly, beginning to drift away. And as they did, the next phase of the ocean story was already taking shape beneath the surface. Hunger is one of the oldest forces shaping life in the ocean. and in the Age of Giants it became a constant, ever-present pressure. Not hunger in the sense of starvation, but hunger as momentum. Hunger as the need to keep growing, to keep feeding, to sustain bodies that had become immense and costly to maintain. In this world, survival was no longer just about avoiding death. It was about consuming enough energy, often enormous amounts of it, to remain viable. And this is where teeth and jaws changed everything. Long before the first massive predators appeared, early marine animals fed in simple ways. They filtered particles from the water, absorbed nutrients through their skin, or engulfed smaller organisms whole. These methods worked well when life was small and competition was limited. But as bodies grew larger and ecosystems became more crowded, feeding had to become more efficient, more specialized, and more aggressive. The evolution of jaws marked one of the most significant turning points in the history of life. Jaws allowed animals to bite, grasp, tear, and crush. They allowed for active hunting instead of passive feeding. They allowed predators to subdue prey larger than themselves. And once jaws appeared, they spread rapidly through marine ecosystems. In the prehistoric oceans, jaws did not evolve just once. They emerged in multiple lineages, each time opening new possibilities. Some jaws were designed for speed, snapping shut quickly to catch agile prey. Others were built for power, capable of crushing shells or breaking bone. Still others evolved into elaborate filtering structures, allowing massive animals to harvest tiny organisms in vast quantities. As bodies grew larger, jaws followed. A large animal without an effective feeding mechanism would quickly starve. Size demanded efficiency. A bigger body meant more tissue to sustain, more energy to circulate, more heat to manage. Every additional kilogram increased the daily cost of survival. This created immense pressure to evolve feeding systems that could keep up, and so, jaws became larger, stronger, and more specialized. In some lineages, teeth became serrated, forming natural blades designed to slice through flesh. In others, teeth became blunt and rounded, ideal for crushing armored prey. Some species evolved multiple rows of teeth, ensuring that damaged or lost teeth were constantly replaced. Others developed interlocking structures that prevented prey from escaping once caught. The variety was staggering. But beneath this diversity was a common theme: efficiency. A predator that could extract more energy from each kill had a significant advantage. One that could subdue prey quickly reduced the risk of injury. One that could feed on a wide range of animals was less vulnerable to fluctuations in prey populations. This drove an escalation in feeding adaptations that mirrored the arms race happening throughout the ocean. Prey species responded in kind. Shells thickened, exoskeletons hardened. Some animals developed spines or bony plates, others evolved speed or camouflage. Still others grew larger, hoping that sheer mass would make them unappealing or impossible to kill. But predators adapted again. Larger jaws meant greater bite force. Stronger muscles allowed for wider gapes. Changes in skull structure improved leverage. Over time, some predators developed skulls that were essentially biological machines, optimized entirely for feeding. In the ocean, feeding is not just about killing. It is about energy transfer. Every bite represents the movement of energy from one organism to another. The more efficient that transfer, the more successful the predator. This is one reason why the largest marine animals often occupy the top of food chains. They're not necessarily the most aggressive or fastest, but they are the most efficient at converting food into survival. Some of the greatest giants of the prehistoric seas were not hunters in the traditional sense at all. They were filter feeders, consuming vast quantities of small organisms. Their jaws were not weapons but tools of collection. Massive mouths opened wide, drawing in water and straining out tiny prey by the millions. This strategy is only possible at large scales. A small filter feeder cannot gather enough food to sustain itself, but a large one, moving slowly through nutrient-rich waters, can accumulate enormous amounts of energy with relatively little effort. This is why some of the largest animals in history did not need teeth at all. Others, however, went in the opposite direction. They became apex predators, relying on strength, speed, and fear. Their jaws became symbols of dominance. Their teeth were tools of both killing and intimidation. Their very presence altered the behaviour of everything around them. In these animals, hunger shaped not just anatomy, but behaviour. They hunted strategically. They selected prey carefully. They conserved energy when possible and expended it explosively when necessary. Their lives revolved around the balance between intake and expenditure, between risk and reward. And because they were so large, the stakes were high. A failed hunt for a small animal might mean inconvenience. A failed hunt for a giant could mean starvation. This pressure refined hunting strategies over millions of years, producing some of the most efficient predators the planet has ever seen. Even scavenging played a role. Not every large predator hunted constantly. Some relied on finding carcasses left behind by others. In an ocean filled with massive animals, death itself became a resource. A single carcass could feed multiple large organisms for extended periods. This created a secondary economy of feeding, one based not on pursuit but on opportunism. It also reinforced the importance of size, since larger animals were better able to defend carcasses or exploit them fully. The relationship between teeth, jaws, and hunger also shaped how animals interacted socially. Some predators hunted alone, others moved in loose groups. Some may have cooperated, while others tolerated each other only briefly. The fossil record offers hints but few certainties. What is clear is that feeding strategies influence social behaviour just as much as anatomy. And underlying all of this was the constant need to eat. Hunger did not sleep, it did not pause. It was the force that kept these massive bodies in motion. Even in the cold depths, even in stable environments, the demand for energy never disappeared. This is one of the reasons why the rise of ocean giants was both impressive and precarious. The larger the animal, the more it depended on the stability of its ecosystem. A drop in prey populations could ripple upward with devastating effects. A change in ocean temperature could alter food distribution. A shift in currents could break feeding patterns that had existed for millions of years. Yet during the height of the age of giants, these systems held. The oceans were productive enough, the climate was stable enough, the food webs were deep enough. Teeth grew larger, jaws grew stronger, hunger drove evolution forward, and as long as energy continued to flow, the giants endured. But hunger is also unforgiving. It does not allow for complacency. It does not wait for adaptation. When conditions change, hunger becomes the force that exposes weakness. A predator that cannot find food dies. A species that cannot adapt disappears. No amount of size or strength can overcome a lack of energy. This truth would eventually catch up with the giants of the sea. But for now, in this chapter of Earth's history, hunger was not an enemy. It was the engine of growth. The pressure that pushed life to its extremes. The reason jaws grew wide and teeth grew sharp. The reason the oceans, for a time, belonged to creatures of unimaginable scale. And as the seas continued to shift, as climates changed and currents reorganized, that same hunger would begin to reshape the world once again, setting the stage for what came next. There was a long stretch of Earth's history when the world above the waves was quiet in a way that feels almost impossible to imagine now. No birds crossed the sky, no mammals walked the shores, no forests rustled in the wind. The land was largely empty, shaped by rock, wind and water, while the real drama of life unfolded far below the surface. The ocean, at this time, was not just the dominant environment on the planet. It was the only place where complex life truly thrived. And in its depths, far from sunlight and weather, enormous creatures moved through the darkness, unseen and unchallenged by anything above. This contrast between silence at the surface and abundance below is one of the most striking features of prehistoric Earth. For millions of years, the most powerful animals on the planet never breached the waves. They did not roar or leave footprints. They lived and died in a realm that left almost no trace for anything above to notice. If you had stood on an ancient shoreline during this era, the ocean might have appeared calm, even empty. Gentle waves, a quiet horizon, perhaps the occasional ripple or distant splash. Nothing to suggest that beneath that surface moved predators larger than buses, animals capable of crushing bone, swallowing prey whole, or filtering entire ecosystems through their bodies. The surface told only part of the story. Below it, the ocean was alive with motion. This separation between the world above and the world below created a unique dynamic. On land, life was still limited, fragile and slow to diversify. In the sea, evolution had already accelerated, producing complexity on a scale that would not appear on land for tens of millions of years. This imbalance mattered. With no competition from land-based predators and no interference from terrestrial ecosystems, marine life evolved in relative isolation. The ocean became its own universe, governed by its own rules, free to explore size, form and behaviour without outside constraint. And because so much of this life existed far from the surface, it evolved in ways that favoured darkness, pressure and silence. Vision changed. In shallow waters, eyes adapted to detect light and colour. In deeper regions, eyes grew larger or vanished altogether. Some species evolved bioluminescence, producing their own light in the darkness. Others relied on vibration, pressure, or chemical cues to sense their environment. Sound became important. Water carries sound far more efficiently than air. Movement echoed. Heartbeats vibrated through the depths. Large animals could detect each other from great distances without ever seeing one another. This silent communication shaped behaviour in subtle ways. Predators learned to move carefully, conserving energy and avoiding unnecessary noise. Prey learned to freeze, to blend in, to disappear into the background. Entire ecosystems operated in near silence, broken only by the distant movements of massive bodies passing through water. And those bodies were vast. Some of the largest marine animals ever to exist spent most of their lives far below the surface, where light barely reached. They did not need to see clearly. They did not need speed. They relied on size, strength, and patience. In these depths, the absence of light created a strange kind of freedom. Without visual cues, camouflage mattered less. Colour lost its importance. Shape and motion became more significant. Many deep-dwelling giants evolved forms that seem alien to us: elongated bodies, reduced features, immense jaws or sensory organs tuned to vibrations rather than sight. This environment also reduced competition. Few animals could tolerate the pressure, cold, and darkness of the deep ocean. Those that could found themselves in a world with fewer rivals and fewer threats. Food was scarcer, but so was danger. This scarcity further encouraged large size. A large animal could travel long distances to find food. It could survive long periods between meals. It could store energy in fat and muscle. It could afford patience. In contrast, smaller animals struggled to persist in such conditions unless they were highly specialized. Over time, this led to a vertical stratification of life. Smaller, faster organisms dominated surface waters. Larger, slower ones occupied deeper zones. The deepest regions became the realm of the giants. And because these depths were largely insulated from surface changes, the creatures that lived there changed slowly. Their world was stable, predictable, and quiet. This stability allowed some species to persist for extraordinary lengths of time with very little change. Lineages endured for millions of years, refining their forms without needing dramatic adaptation. It also meant that when change finally did come, it arrived as a shock. But for much of this era, the ocean's depths were a kind of sanctuary. The monsters of the deep did not need to compete with terrestrial life. They did not need to contend with storms, fires, or droughts. Their world was governed by different rhythms, slower and more deliberate. Even the concept of day and night held little meaning below a certain depth. Life existed in a perpetual twilight or darkness, where time was measured not in hours but in seasons and migrations. This created a sense of timelessness that is difficult to grasp. Generations passed slowly, reproduction was infrequent, growth was gradual, the pace of life was unhurried. And yet, these creatures were not fragile. They were among the most resilient organisms ever to exist. Their resilience came from their environment. The deep ocean is one of the most stable places on Earth. Temperatures fluctuate little. Salinity remains constant. Light is absent but predictable in its absence. There are no sudden freezes or heat waves. No storms, no wildfires, no droughts. This stability allowed life to invest in longevity rather than speed. And longevity, combined with size, created dominance. The giants of the deep did not need to fight often. They did not need to flee. Their presence alone was enough to shape their surroundings. Smaller animals adjusted their behaviour simply to avoid crossing paths with them. This is one of the reasons why so many of these creatures left such limited fossil evidence. They did not congregate in large numbers. They did not live near shorelines where fossilization is more likely. They lived and died in deep water, where remains were quickly consumed or buried beyond reach. To us they seem almost mythical, but to the oceans of the time, they were normal. What makes this period especially fascinating is how disconnected it was from what was happening on land. While giant predators ruled the seas, terrestrial life remained relatively modest. Early plants and animals were still establishing themselves. There were no towering forests, no massive herbivores, no large carnivores. The centre of biological power was underwater. This imbalance would eventually shift, but for a long time, the ocean held the crown. The silence above and the monsters below existed together. Two worlds moving at different paces. And then, slowly, that balance began to change. As continents drifted, as climates shifted, as oxygen levels fluctuated, the quiet stability of the deep began to erode, subtle at first, barely noticeable, but enough to disrupt the delicate systems that had supported giant life for so long. Currents changed direction, nutrient flows altered, temperature gradients shifted, areas that had once been rich grew sparse, feeding routes lengthened, reproductive cycles were disrupted. The giants did not vanish immediately. They endured. They adapted where they could. But the world they depended on was no longer the same. And while the surface remained calm to any casual observer, the deep ocean was entering a period of quiet stress. The silence was still there, but it carried a different weight. Because in nature, silence often comes before change. And in the depths of the prehistoric oceans, that change was already underway, setting the stage for a slow and irreversible transformation of life beneath the waves. There was no single moment when the giants vanished, no great final battle, no sudden darkness, no line in the water where the age of titans ended and something else began. What happened instead was quieter, slower, and far more typical of how life on Earth actually changes. The giants began to fade not because they were weak, but because the world around them was no longer the one they had evolved to master. At first, the changes were almost imperceptible. Currents shifted slightly, altering the way nutrients moved through the oceans. Temperature gradients changed, not dramatically, but enough to affect where plankton bloomed and where it did not. Oxygen levels fluctuated, rising in some regions, falling in others. None of these changes alone would have doomed the giants, but together, layered over thousands and then millions of years, they began to strain the delicate balance that had allowed such immense life to exist. The ocean, once predictable in its rhythms, grew less so. One of the first signs of trouble came from the bottom of the food chain. Plankton, the tiny organisms that form the base of nearly all marine ecosystems, are extraordinarily sensitive to environmental change. Slight shifts in temperature, acidity, or nutrient availability can cause blooms to expand or collapse. When plankton populations changed, everything above them felt the effect. For small animals, these changes were disruptive but survivable. They could adapt quickly, reproduce rapidly, and exploit new niches. For giants, the story was different. Large bodies require consistency. A giant predator or filter feeder cannot simply switch diets overnight. It cannot relocate quickly if its food source disappears. It cannot reproduce fast enough to evolve new traits in response to sudden environmental pressure. It depends on stability, on predictability, on systems that change slowly. As the oceans began to lose that stability, the giants began to struggle. Some species found their feeding grounds shrinking. Others found their prey becoming scarcer or migrating to new regions. Still others faced changes in water temperature that affected their metabolism and reproduction. None of these pressures were dramatic on their own, but together they formed a kind of slow attrition. The giants did not collapse, they dwindled. At the same time, the world itself was changing in larger ways. Continents drifted, ocean basins opened and closed, sea levels rose and fell. These geological processes reshaped currents and altered the distribution of heat and nutrients across the planet. Areas that had once been rich feeding grounds became barren. New regions opened up elsewhere, but the transition was rarely smooth. For animals that depended on long, stable migratory routes or consistent seasonal patterns, this was devastating. The deep ocean, once a refuge of stability, began to feel the effects as well. Changes in surface productivity reduced the amount of organic matter sinking into the depths. Food became scarcer. The slow rain of nutrients that had sustained deep-sea giants thinned. In a world where energy was already hard to come by, this mattered enormously. Another factor began to play a role: competition. As some giant species declined, others tried to fill the gaps. Smaller, more adaptable predators expanded into niches once dominated by giants. These animals required less food, reproduced more quickly, and could respond faster to environmental change. In evolutionary terms, they were more flexible. This shift favoured agility over size, speed over mass, versatility over specialization. The giants, for all their power, were specialists. They were optimized for a world that no longer existed. And then there were the larger disruptions. Mass extinction events, triggered by volcanic activity, climate shifts, or changes in ocean chemistry, periodically swept through the planet. Some were relatively mild, others catastrophic. Each one reshaped life in profound ways. For small organisms, these events were survivable. Their populations could rebound quickly. Their genetic diversity allowed for rapid adaptation. For giants, extinction events were devastating. Large animals require long periods to reach maturity. They reproduce slowly. Their populations are naturally small. When disaster strikes, they have little buffer. A sudden drop in food or a rapid environmental shift can wipe out entire species before they have a chance to recover. This pattern repeated throughout Earth's history. After each major disruption, the oceans would recover. Life would return. New species would emerge. But the giants that once dominated rarely came back in the same form. Instead, new lineages would arise, often smaller, often more flexible, sometimes building toward large size again, but never quite replicating the old balance. Another subtle but important factor was oxygen. Although oxygen had once enabled gigantism, its levels were never constant. Periods of high oxygen supported large bodies, but declines made those bodies harder to sustain. Even small drops in oxygen concentration can have outsized effects on large animals, whose tissues require vast amounts of it to function. As oxygen levels fluctuated, the margin for survival narrowed. Some giants adapted by slowing their metabolism further. Others retreated into deeper or colder waters. Some likely became more migratory, following optimal conditions as they shifted across the globe. But adaptation has limits. Eventually, the cost of being large began to outweigh the benefits. At the same time, life on land was beginning to change in ways that would eventually ripple back into the sea. Plants spread across continents, altering atmospheric composition and weather patterns. Soils developed. Rivers carried different nutrients into the oceans. Erosion rates changed. All of this affected marine ecosystems in ways that unfolded slowly but inexorably. The ocean was no longer the isolated, self-regulating system it had once been. And as conditions became more complex, the advantage shifted away from giants and toward organisms that could respond quickly to change. Smaller fish diversified. New predators emerged. Marine mammals, much later, would inherit some of the roles once held by ancient giants, but in a very different ecological context. The disappearance of the great ocean titans was not a tragedy in the dramatic sense. It was not sudden or violent. It was simply the natural consequence of a world that had moved on. Evolution does not preserve what is impressive. It preserves what works, and for a long time, enormous size worked beautifully. But when the rules changed, when stability gave way to variability, when energy became harder to predict, size became a liability rather than a shield. The giants faded quietly, leaving behind bones buried in sediment, impressions in stone, and subtle signatures in the structure of modern ecosystems. Their absence reshaped the ocean. Food webs became shorter. Energy flowed through smaller, faster cycles. Ecosystems became more dynamic, more responsive, but also less capable of supporting truly massive life. In a sense, the ocean became more alive, but less grand. And yet, traces of the old world remained. Even today, the largest animals on Earth live in the sea. Whales, though smaller than some of their prehistoric predecessors, are reminders of what the ocean can produce when conditions allow. Giant sharks, deep-sea squids, and other massive creatures echo a time when size ruled absolutely. They are not anomalies. They are survivors of a pattern that once dominated the planet. The fading of the giants was not an ending, but a transition. It marked the shift from an age defined by sheer scale to one defined by adaptability, from slow, towering life forms to faster, more flexible ones. From oceans ruled by titans to oceans shaped by balance. And as the seas continued to change, as climates cooled and warmed, as continents drifted and currents rearranged, the story of life moved forward, carrying with it the memory of giants that once ruled the depths. Their time had passed, but their influence remained. Because even in absence, they shaped what came after. And in the quiet spaces they left behind, new forms of life began to rise, shaped by a world that no longer belonged to giants alone. Even though the age of the great ocean titans has long passed, their presence has never truly vanished. It lingers in ways that are easy to miss, woven into the structure of modern seas, echoed in the bodies and behaviours of creatures that still move through today's waters. The giants may be gone, but the ocean remembers them. You can see it first in scale. Modern oceans still produce animals far larger than anything found on land. Blue whales, the largest creatures to ever exist, glide through the water with the same effortless authority once held by prehistoric titans. Giant squid haunt the depths, rarely seen but unmistakably shaped by the same pressures that once created colossal predators. Even large sharks, though smaller than their ancient relatives, carry echoes of an older world in their proportions and movements. These animals are not accidents. They are not evolutionary outliers. They exist because the ocean still operates under many of the same physical and biological rules that once allowed giants to thrive. Water still supports mass. Currents still move energy across vast distances. Plankton still blooms in enormous quantities. Depth still offers refuge. Cold still slows time. The difference is not in the rules themselves, but in how tightly they are now constrained. Where prehistoric oceans were expansive and relatively stable for long stretches, modern oceans are more fragmented. Currents shift more rapidly. Climate changes occur faster. Human activity adds layers of disruption that did not exist before. The The system still functions, but with far less margin for error. And yet, within those constraints, the echoes remain. Consider whales. Their size alone tells a story that stretches back hundreds of millions of years. They are not simply large mammals that return to the sea. They are inheritors of an ecological role shaped long before mammals existed. Their feeding strategies, migration patterns, and even social behaviours reflect the same principles that governed ancient giants. They feed where productivity is high. They migrate along nutrient-rich routes. They rely on vast amounts of food to sustain enormous bodies. They reproduce slowly. They live long lives. They are vulnerable to sudden environmental change. In all of this, they mirror their ancient predecessors. Even the way whales move carries echoes of deep time. Their slow, powerful tail strokes are optimized for efficiency, not speed. Their bodies are shaped to glide rather than sprint. Their mass works with the water, not against it. These are not modern innovations. They are ancient solutions, refined over millions of years. The same can be said of deep-sea creatures. In the darkest parts of the ocean, where sunlight never reaches, life still follows patterns established long ago. Large, slow-moving animals drift through cold water. Metabolism remains low, growth is gradual, lifespans are long. Many deep-sea species today have close analogues in prehistoric forms. Some look so similar to ancient fossils that it is difficult to tell them apart without careful study. They are living reminders that, in certain environments, evolution does not rush. It refines. It preserves. Even behaviours echo the past. Modern predators still rely on ambush, patience, and sudden bursts of power rather than prolonged chases. Many species still follow migratory routes that align with ancient current patterns. Some feeding grounds used today may have been used for millions of years by different animals filling the same ecological roles. The ocean has memory, not in the conscious sense, but in its structure, where nutrients rise, where currents converge, where life flourishes or fades. These patterns endure, shaping which creatures can thrive and which cannot. There is also an echo in absence. The oceans today feel quieter in a way that is difficult to quantify, not silent, but diminished. The sheer biomass of large animals is far lower than it once was. The number of truly enormous creatures has dwindled. The gaps left behind by extinct giants have never been fully filled. This absence changes everything. Without massive predators to shape behaviour, prey species behave differently. Without enormous filter feeders, nutrient cycles shift. Without giant carcasses sinking to the seafloor, deep-sea ecosystems lose one of their richest food sources. Scientists have only recently begun to understand how important these giants were, not just as individuals, but as ecosystem engineers. When a massive animal moves through water, it stirs nutrients. When it feeds, it redistributes energy. When it migrates, it links distant regions of the ocean. When it dies, it provides a feast that can sustain life for decades. Remove enough of these animals, and the entire system subtly changes. This is one reason modern oceans behave differently from prehistoric ones, even when temperature and chemistry appear similar. The architecture of life itself has shifted, and yet, despite all this change, the potential for gigantism has not vanished. The ocean still has the capacity to produce enormous life. It still has the depth, the volume, and the energy. What it lacks is stability over long time scales. In the past, conditions could remain favourable for millions of years. Today, change happens in centuries or even decades. That pace favours small, fast-reproducing organisms. It punishes slow-growing giants. This is why modern large marine animals are so vulnerable. They live in a world that no longer matches the rhythm of their biology. Whales cannot adapt quickly to shifting prey distributions. Sharks cannot reproduce fast enough to recover from population losses. Deep-sea creatures cannot escape changes in temperature or chemistry. They are living echoes of an older world, surviving in a present that no longer fully supports them. And yet, Their persistence is remarkable. Despite industrial fishing, climate change, noise pollution, and habitat disruption, many of these animals continue to exist. They migrate, feed, reproduce, and endure. They carry within their bodies the legacy of oceans that once belonged entirely to giants. When we encounter them, even briefly, something instinctive seems to stir. A sense of awe, a feeling that we are looking at something ancient, something that does not quite belong to our time. That reaction is not accidental. Humans evolved in a world where the largest creatures were already gone. We have no cultural memory of living alongside true ocean titans, and yet, when we see a whale breach or a massive shark glide past, we feel it immediately. Scale does something to the mind. It reminds us that life once operated on different terms, that the world was once larger, slower, and less constrained, that our moment in time is just one chapter in a much longer story. The echoes of the giants also live on in the scientific record. Fossils reveal patterns that repeat across eras. Periods of stability give rise to large forms. Periods of disruption favour smaller ones. Again and again the same cycle appears. This suggests that gigantism is not an evolutionary anomaly, but a recurring phase in the history of life. Given the right conditions, it returns. Whether it will ever return on the same scale is an open question. Modern environmental pressures make it unlikely in the near future. But over geological time, nothing is fixed. Oceans shift. Climates change. Life adapts. The story is not finished. For now, the giants exist mostly in memory, fossilized in stone and hinted at in the bodies of modern animals. They exist in the deep sea, in rare sightings, in the shape of bones too large to belong to anything alive today. They exist in the way the ocean still feels vast and unknowable, no matter how much we explore it. And perhaps most of all, they exist in the way we think about the sea itself. When we imagine the ocean as mysterious, powerful and ancient, we are responding to a truth embedded deep in its history, a truth shaped by millions of years of giants moving through dark water, shaping ecosystems, dominating food webs, and leaving behind a legacy that still resonates. The ocean has changed, but it has not forgotten what it once was, and as long as water covers most of this planet, as long as currents move and life adapts, the echoes of the giants will remain, drifting silently beneath the waves, reminding us that the world we see is only the latest version of something far older, far larger, and far more patient than we can easily imagine. Time behaves differently when you look at it through the lens of giants, not because time itself changes, but because scale changes how we understand it. When we think in days or years, even decades, everything feels immediate, urgent. But the existence of creatures that live for centuries, evolved over millions of years, and dominated ecosystems for spans longer than human civilization has existed, forces a different perspective. The giants of the ocean were not just large in body, they were large in time. Their lives unfolded slowly. Their rise took millions of years. Their dominance lasted longer than most species ever experience, and their disappearance, when it came, was not sudden, but drawn out across ages. In their story, time is not something that rushes forward. It stretches, bends, and accumulates. One of the most striking lessons the giants teach us is that stability matters more than speed. The largest marine animals did not thrive because they evolved quickly. They thrived because the world around them changed slowly enough to allow gradual adaptation. Their bodies were built for consistency. Their strategies depended on predictability. Their success was tied to long, uninterrupted spans of environmental balance. This is the first quiet truth the giants reveal. Life can grow enormous only when time is generous. When conditions remain steady, evolution favours refinement rather than reinvention. Traits are polished rather than replaced. Bodies grow larger, more efficient, more specialised. Energy flows settle into reliable patterns. ecosystems become layered and interdependent, the giants were not rushing toward dominance. They arrived there simply by enduring. That endurance carries an important implication. It tells us that progress in nature is not always about innovation. Sometimes it is about persistence, about surviving long enough for small advantages to accumulate, about existing in harmony with conditions that allow growth to outpace disruption. The giants also teach us that time does not reward excess. As long as the resources were abundant and stable, size was an advantage. But the moment conditions shifted, that same size became a burden. Large bodies could not adjust quickly. Long lifespans meant slow adaptation. Dependence on specific food chains created vulnerability. In this way, the giants reveal a deeper truth about time and life. What works over long periods can fail suddenly when the pace of change increases. This is not a moral lesson, it is a structural one. Evolution does not favour the strongest or the largest. It favours those that match the tempo of their environment. When the rhythm of the world changes, survival depends on how quickly a species can adjust its own tempo to match. The giants could not. Their bodies were tuned to a slow world. When the world sped up, they were left behind. Another lesson emerges when we consider how long the giants remained dominant. Their reign did not last a few generations or even a few thousand years. It lasted tens of millions of years. Entire geological periods passed under their rule. Continents drifted, climates shifted, sea levels rose and fell, and still they endured. This challenges the way humans often think about permanence. We tend to assume that what exists now will continue, that the present is a stable reference point. But the giants remind us that even the most successful forms of life are temporary. Dominance is not destiny, it is a phase. Time eventually erodes everything, not through violence, but through accumulation. Small changes layered on top of one another until the old balance no longer holds. The giants also show us that extinction is not always dramatic. There were no final battles, no singular disasters that wiped them out all at once. Instead, populations declined gradually, ranges contracted, reproduction slowed, species faded quietly from the record. This slow disappearance is perhaps more unsettling than sudden extinction. It suggests that loss does not always announce itself. It can unfold invisibly, masked by the illusion of continuity. By the time the giants were truly gone, the world had already moved on. Another lesson lies in the relationship between size and time. Large animals experience time differently than small ones. Their heartbeats are slower. Their metabolisms run at a different pace. Their lives stretch across longer spans. In a sense, they exist in a slower version of reality. This difference in biological time shapes behaviour. Large animals tend to be cautious. They invest in longevity. They avoid unnecessary risks. Their strategies are long-term. The giants of the sea embodied this principle. They did not rush. They did not overextend. They conserved energy, moved deliberately, and relied on consistency rather than speed. In contrast, small organisms live fast. They reproduce quickly, they adapt rapidly, they respond immediately to change. When the world is stable, slow life thrives. When the world becomes unpredictable, fast life takes over. This pattern repeats throughout Earth's history, and it is still playing out today. The giants also teach us something about limits. There is a point at which growth stops being beneficial, a point at which additional size no longer offers protection or efficiency. Beyond that point, the cost of maintenance outweighs the advantages gained. The prehistoric oceans approached that limit. When food webs were deep and energy abundant, size made sense. But once those systems thinned, even slightly, the balance tipped. The largest animals were the first to feel the strain. This tells us something fundamental about how life operates over long spans of time. There are ceilings as well as floors. Evolution explores them both, Perhaps the most profound lesson the giants leave behind is one of humility. They remind us that Earth has hosted worlds far different from our own. Worlds where animals larger than anything alive today were ordinary. Worlds where ecosystems functioned on scales we struggle to comprehend. Worlds that lasted longer than human history by orders of magnitude. And yet those worlds passed. Not because they were flawed, but because time moved on. The giants did not fail. They completed their chapter. Their existence shows that life is not marching toward a single goal. It is exploring possibilities, testing forms, filling niches, then moving on when conditions change. We are part of that same process. Our own species exists within a narrow window of time, shaped by circumstances that could shift as easily as those that once favoured the giants. The lesson is not that extinction is inevitable, but that nothing is guaranteed permanence. The ocean, perhaps more than any other environment, makes this clear. It preserves memories in its depths. It records history in layers of sediment. It holds the remains of worlds long gone, and yet it never stops moving. The giants teach us that time is not an enemy, but it is indifferent. It does not reward ambition or punish failure. It simply unfolds, carrying life along with it. To exist within time is to be temporary. To understand time, as the giants did, is to accept that scale and endurance matter more than speed and dominance. Their story invites us to look beyond our immediate concerns and see ourselves as part of a much longer continuum. One in which rise and decline are natural, where change is constant, and where even the mightiest forms eventually give way to something new. In that sense, the giants do not teach us how to survive forever. They teach us how to belong to time without needing to conquer it. And as we turn toward the final part of this journey, their lesson lingers quietly beneath the surface, reminding us that the ocean's greatest teacher has never been strength or size, but patience. The ocean has a way of holding on to things, not in the way we remember with stories and names and dates, but in a quieter, deeper sense. It remembers through patterns, through currents that still follow ancient paths, through layers of sediment that record what once lived and died, through the shapes of animals that exist today, carrying echoes of forms that vanished long before the first human ever looked out over the water. Even now, if you stand at the edge of the sea and watch the surface move, you're looking at something impossibly old. Older than any city, older than any language, older than memory itself. And beneath that surface, hidden by depth and distance, are the remnants of a world that once belonged to giants. They are gone now, but they are not forgotten. Their influence lingers in the way the ocean functions, in the way energy moves through food webs, in the way large animals still migrate across entire basins, in the way deep-sea ecosystems depend on rare but powerful events, like the fall of a great body to the ocean floor, echoing the ancient cycles that once defined life below. The ocean still behaves as if giants might return at any moment. Its vastness remains, its productivity persists, its ability to support enormous life, at least in theory, has not vanished. What has changed is time itself, the pace of change, the rhythm of the planet. Where once conditions remained stable for millions of years, now they shift within centuries. Where once ecosystems had time to adapt, now they are forced to react. The ocean still remembers how to build giants, but the world no longer gives it the patience to do so. And yet, when we encounter the largest creatures that remain, something stirs in us. When a whale surfaces, when its body breaks the water in a slow, deliberate arc, there is a pause that happens naturally. Conversations stop, attention sharpens. Even people who know nothing about biology or evolution feel it. A sense of scale, a recognition of something older and deeper than everyday life. That reaction is not coincidence, it is recognition. Some part of us understands instinctively that these animals represent a lineage far older than ourselves, that they are living reminders of a time when size was not excess, but equilibrium, when life moved at a pace measured in centuries rather than seconds. In a world dominated by speed, the giants feel almost out of place. They move slowly. They take time to grow. They do not rush. They do not multiply quickly. They exist on a timeline that feels incompatible with modern life. And yet, that is precisely what makes them so powerful as symbols. They remind us that not everything meaningful is fast. They remind us that longevity requires balance, that growth without stability leads to collapse, that survival is not about conquering the environment, but aligning with it. The ancient oceans understood this. They provided space, energy, and time. In return, life explored its limits with patience and restraint. When those conditions changed, the giants faded, not because they failed, but because the world had shifted beyond what they were built for. There is something quietly humbling about that. It suggests that success, even on the grander scale, is temporary, that dominance is contextual, that no form, no matter how impressive, lasts forever. And yet, it also suggests something hopeful. Because while the giants themselves disappeared, the principles that created them did not. The ocean still follows the same laws of physics, energy still flows, evolution still experiments, life still adapts. Given enough time and stability, the sea could once again give rise to forms we can barely imagine. Perhaps not in our lifetime, perhaps not for millions of years, but the potential remains. That is the quiet promise the ocean carries. It is easy to think of the past as something separate from the present, as if the world of prehistoric oceans ended cleanly and gave way to the one we know now. But the truth is more subtle. The past is layered beneath the present. Every wave carries the motion of ancient currents. Every deep trench holds sediments that were once living ecosystems. Every marine animal carries genetic echoes of ancestors that survived mass extinctions, climate shifts, and planetary upheaval. The ocean does not erase its history, it absorbs it, and in doing so, it becomes a living archive of time itself. When we talk about the giants, we are not just talking about large animals, we are talking about a way the world once worked, a set of conditions that allowed life to stretch to its limits, a reminder that Earth is not static, and neither is life. There is a tendency to view extinction as failure, but the story of the giants suggests something different. It suggests transition, adaptation, the passing of one era into another. The ocean did not mourn the giants, it adjusted. New species emerged, new relationships formed, new balances took shape. The system continued, reshaped, but alive. And in that sense, the giants never truly left. They exist in the bones of whales, in the deep sea scavengers that still rely on rare, massive foodfalls, in the way nutrients cycle through the water, in the way the ocean still favours patience, efficiency, and scale. They exist in the questions we ask when we look at the sea and wonder what else might be down there. They exist in the quiet feeling that the ocean is larger than our understanding, older than our stories, and far more complex than we can fully grasp. And perhaps that is their final lesson, that the world is not built for us alone, that we are temporary participants in a much longer narrative, that what seems permanent is often only a moment in deep time. When you listen to the ocean, truly listen, you can almost sense it. Not voices or sounds, but presence, continuity, a sense that something vast is still unfolding just out of sight. The ocean still remembers its giants. It remembers how to build them. It remembers how they moved. It remembers the balance that sustained them. And as long as the sea exists, as long as currents flow and life adapts, that memory will remain, waiting quietly beneath the surface, part of a story that never truly ends. So wherever you are right now, whatever time it is in your part of the world, know that you are connected to that story. That the water you see, the air you breathe, and the rhythms of life around you are shaped by events that began long before anyone was here to witness them. The giants may be gone, but the ocean remembers, and in its vast, patient way it always will.